All right, so I'm Alex Dunyak, and I'll be presenting my PhD research seminar, Linear Stochastic Graphon Systems with Q-noise. Now, there are four main topics that we're going to discuss today. First, we're going to talk about just some background information. What is the motivation for studying graphons and large graphs in general? What are graphons? Because it's not a particularly common research subject. And how do we add stochastic noises to these networks? And this is introduce what we call Q-noise. And finally, we'll overview some results that we had in the 2022 Conference on Decision and Control, where we had feedback control of these Q-noise graphon systems. So from there, we're going to introduce some new research into the linear quadratic Gaussian optimal control of these stochastic graphon systems. We'll explore a special case where when the graphon is low rank, the system can be controlled exactly in finite dimensions. And finally, we'll explore something that we call graphon field games, which are a type where each node on the graph is a player in a game, and they are trying to optimize with respect to the other players in a discrete time dynamic system. So large graphs are obviously very common in engineering contexts. For example, you have transit and logistics networks where you're trying to optimize the amount of goods that you ship from one location to another. You have electrical generation and distribution. You have the Internet of Things where you're trying to coordinate these large networks of devices so that they give you feedback into the state of society. And you have, and in a more general sense, you have social networks and markets that you can analyze and predict events from. Now on the right here, we have this map of the airline connections in the United States, circa 2008. Each node in the graph is an airport, and each line represents a route flying to and from that airport. So it's clearly a large, complicated graph. It's not simple to write down, but we want to analyze this graph, so we need some method of addressing this. So the type of system that we're going to be interested in, mostly working with specifically, are what we call graph averaging systems, introduced by Gao and Peter Caines a few years ago. So the idea is that you have a vector of states where each node has a local state. And further, you have a vector of controls where each node has its own local control. And you have two weighted adjacency matrices, AN and BN, which describe the impact of the states globally over the network. And what you end up with, and a graph averaging system is a system where you have this linear differential equation with this AN, this local effect, this AN times XI, plus the average over the adjacency matrix that your specific node I is connected to. And similarly for the local control, beta times UI plus the average over the second adjacency matrix BN, which you can of course just compactify into a single vector of states. So the fundamental difficulty with this is that AN and BN can be very large, and you might not know their specific structure. So how do you address this? Now, the work that our lab's been doing is the use of graphons to address this. Now, graphons are these sorry, trying to move the thing out of the way. So graphons are just measurable functions on the unit square, mapping the unit square to some from 0 to some positive bound. And the example here is the uniform attachment graph, which is a specific type of randomly generated graph sequence, which has a convergent graphon. So here in the middle, you have a picture of one uniform attachment graph sequence. The first node is the most connected, and when you look at the adjacency matrices of these of the graph sequence for 50, you see that there might be there is a pattern, but it's not very clear what the pattern is. It looks somewhat arbitrary. Then
can you close the bar on the left as it's obscuring some of the mathematics?
Oh. Thousand node graph, which again, it's a complicated adjacency matrix. As you can see through the because there are a lot of isolated points. But when you take the graphon limit, you can actually approximate the limit of the adjacency matrix with this smooth graphon. In this case, it's just the function for alpha and beta of 1 minus the max of alpha and beta. So the most general type of convergence for these graphs is in the cut metric sense, but we're going to use the topology of the convergence of these adjacency matrices and as L2 operators on the unit square. So there are some other standard graphs. We're not going to go too into detail, but we might just have for example, an Erdős, some other common graphs that might have a graphon. You have an Erdős-Renyi graph. It is just the probability of connection is just constant between any two nodes, independent of any other nodes. You could just say that the probability of connection between two nodes on a graph that's defined on a line is just given by the distance between the nodes or some function of the distance between the nodes. Sort of an extension of the Erdős-Renyi graph is the stochastic block matrix, where each node belongs to a set, and the probability of connection between nodes is dependent only on their set. So to define their graphon, you just partition the unit interval into the number of sets you have, and then set the graphon to be piecewise constant on those intervals. And finally, the special case we'll look at later, when the graphon W has a finite number of eigenfunctions, then you can actually explicitly write W as the sum of the finite sum of this f of alpha times f of beta for the k eigenfunctions. So the general approach we're going to use for this control is just to write. We're going to take the finite graph system here in the middle. And for the finite graph system on the top, we're going to map it to the piecewise constant functions on the unit interval and unit square. And then we're going to say that in the limit, as the number of nodes in the graphs goes to infinity, it converges to this graphon system, which is where the adjacency matrices is approximated by this smooth graphon, and the states and the controls are approximated just by L2 functions on the unit interval. So just to rigorize that here, when we take our graph averaging systems and take the limit, we just end up with these deterministic graphon systems. So the graphon is just acting as an integral operator, meaning that you just, for each point alpha, you just integrate from 0 to 1 of the graphon of alpha comma beta, x of beta, d beta. And that's that's just, whenever I say a graphon acting as an operator on a state, that's what I mean. So many standards control system or control theory results hold for these linear and linear infinite dimensional systems, but you can't just make a straightforward IID extension to a stochastic extension to this system. You can't create a probability distribution that satisfies it. So,
sorry, Alex, before you go to the stochastic modeling, I just had a quick clarification question.
yes.
So in your modeling, the parameter alpha is a scalar and not a matrix?
So in our modeling, the parameter alpha is a scalar. It refers to a point on the unit interval.
No, so just like when you write down the dynamics, the top equation on the slide.
Oh, that's
that alpha is so that alpha is not the alpha at the bottom, right?
No, sorry, that should just be an A. That's just
okay. And that's allowed to be that's a matrix valued object, or that's the alpha and beta on that first line are these matrices or scalars?
Alpha and beta on the first line are just scalars. So for the purposes of this talk, we're going to be talking about systems where each node only has a single scalar state. It can be extended to systems where the nodes have multiple states, but then you just get into questions like, do you have multiple graphons relating to multiple states?
Perhaps you could say multiple indices, because the X is a state in a dynamical sense.
No, but I do mean that the nodes in the graph have multiple states, as being separate from the nodes in the graph having multiple indices.
Yeah, but the alpha, not that alpha, but the alpha of the graphon is a scalar index between 0 and 1.
Yes.
So maybe the word index avoids all.
Yes, maybe.
Right, thanks.
All right, so when we have these Q-noise, these Q-wiener processes here, we just need to define some formalism. We need have to start with a Hilbert space. So the one we're going to be talking about here is just the space of square integrable functions with the standard induced norm from the inner product on the unit interval given here. Then we need a covariance operator. So we define this Q, which is as a positive self-adjoint operator with specifically summable eigenvalues and an orthonormal basis of eigenfunctions. And finally, we need one more thing. We need a collection of independent standard Wiener processes. Now, we're not trying to create a probability distribution for this infinite collection of Wiener processes. We're just using them as part of our construction. So we can create our Q noise here as this W process as a function of omega, time, and the spatial index alpha, which is just the sum over the root of each eigenvalue of Q times times one of the orthonormal eigenfunctions evaluated at alpha times the one of the independent standard Wiener processes. And because of the scaling by the eigenvalues and the orthogonality of the eigenfunctions, this is a valid probability measure, and you can use it for stochastic calculus. So in the literature, this is often called a Q-Wiener process. In our talk here, we're going to call it a Q-noise. So we have a few simple properties for these that we're going to require these to have. We're just going to say that they are measurable random variables over the spatial index alpha, a finite time interval, and the set omega. Further, they have Brownian motion increments for a fixed alpha and over the time interval t to s, given by this this first equation. Then they have the covariance that you would expect if you have two time intervals between 2 points. The covariance is the overlap of the time intervals times the covariance operator Q evaluated at the 2 points. And finally, they're just we're going to require them to be piecewise continuous almost everywhere, and Bochner integrable, which is just an extension of the Lebesgue integral. So just as a couple examples here, we have if we have the covariance operator on the top left is just given by the cosine of pi times alpha minus beta. We can show a sample path of the Q noise on the top right, where you can see that that locally the system is very highly correlated over the graphon parameter here. And in the bottom left, we see a uniform attachment graphon that we talked about somewhat earlier. And when we have a Q noise with using the uniform attachment graphon as the covariance operator, you see that it's correlated locally near 0, but as you get farther towards away from 0, it becomes less and less correlated locally. So this is the theorem presented in the CDC 2022. But when you have an n-node graph averaging system, but with states denoted xn, satisfying this stochastic differential equation here, then if you assume that the initial conditions converge, the graphon or the operator an converges to its respective graphon plus some constant along the diagonal, and the Q noise converges, then your sequence of graph averaging systems is Cauchy. And because it's Cauchy and the space of L2 functions is complete, there is a limit process that we denote here x infinity, which you can actually write the explicit solution along a sample path in the bottom here. So from here, we want to move into our standard optimal control world. So we're going to start with just saying, if we take a standard finite graph linear quadratic Gaussian problem on one of our n-node graph averaging systems with a disturbance given by this Wn, which is a normal vector of Brownian motions with zero mean and the Qn covariance. And we have our standard objective linear quadratic objective function being the expectation of this quadratic integral. Then you can find the optimal control by using the linear state feedback and the solution of the Riccati equation. Now, this is very classical control theory in finite dimensions. It's so there's nothing surprising about this result. Now, furthermore, this result has been extended to the space of L2 operators for just with Q-noise or Q-Wiener processes. Whereas here, instead of having a finite dimensional system, you have a flow in a L2 space given by this differential equation in L2 space defined here, and it satisfies this top objective function. objective function where you're trying to minimize the expectation of the quadratic function of these L2 states xt and your L2 valued controls ut. So when you have a full state feedback system, you can use the Riccati equation solution again. It has the same form as the previous Riccati equation, and you end up with these same linear states as this same linear feedback on the state x. So what we have what we're interested in is proving that the graph averaging system indeed converges to the graphon system in the limit, and this is a theorem that we've submitted to the American Control Conference in 2024. But when you have your sequence of graph averaging systems xn and you have your graphon system x satisfying their respective stochastic differential equations, then when the required convergence and boundedness assumptions on all the operators hold, and the initial conditions and the Q-noise, as well as on the cost operators, the strictly positive R and the positive but not strictly positive M's, then you can we can show that actually the two systems do converge, both in cost and in the actual trajectory, which is our result down here. So the way we prove this is just it's somewhat long and involved, but it has three main steps. First we just write this variable delta n here, which is just the difference between the solutions of the operator Riccati equations for the respective systems. Then we show that, and this has the corresponding differential equation delta dot, which is just the difference between the two Riccati equations that S solves. So we show that this delta dot is bounded linearly by delta n plus some function f, which is not a function of delta. Then we just apply Gronwall's inequality to delta n and show that it gives a required bound on delta n, which converges to 0 as n goes to infinity when you assume the convergence of all the underlying operators. And then, because we've shown the Riccati equations converge, we can just directly apply the theorem from CDC because it's a linear state feedback control. So we end up showing that. This operator an minus bn k times x just converges to a minus bk times x. And because this is just some convergent feedback operator, then the result from the 2022 CDC holds. So just as a quick example of to show that this actually does hold as you would expect, we have just a sample run of a few systems here. So on the top, we have a 500 node graph averaging system with randomly generated adjacency matrices, where AN and BN were generated from these two graphons, cosine of pi alpha minus beta and the uniform attachment graphon, and where the covariance of the Q-noise is given by by the uniform attachment graphon as well. Then we can actually, and you see in the top here, the graph averaging system is relatively non-smooth, but it has a known trajectory. Then in the middle here, we're approximating the graphon system on 500 grid points of the unit interval, just by partitioning it into 500 points and then or 500 subintervals, and then taking the midpoint of each interval and evaluating the system on those grid points using the smooth graphons A and B directly, and as well as the same sample path, because we're assuming that the Q-noise converges. And you can see that, yes.
So what's the vertical axis?
Oh, the vertical axis here is just the state of the system for each node at each time. So the graph feature here corresponds to the designation of each node.
So then these are sample paths for.
Yes, each one of these pictures is a sample path. We take one sample path of the Q-noise with this covariance operator here. And then we are using that same sample path for each system, because otherwise these systems would agree in distribution, but not in specific trajectory, which is not very illustrative.
But then the non-smoothness comes from the fact that these are sample paths and not the averaged over different. So there's no expectation acting here.
No, there's not particularly an expectation acting here. But then
it's natural for it to be non-smooth.
Yes, it's expected that it's not smooth. But in particular, the adjacency matrices in the top graph that we're using to do the finite node graph averaging systems are very non-smooth, because as their adjacency matrices, each entry is either 0 or 1. So there's no smoothness there. It's not that the resulting graph picture might be relatively smooth for large enough n, which is what you would expect, but it's not obvious what the structure of the graph is.
All right, thanks.
Yes, and then finally, to just demonstrate why we might want to use this graphon approach. Again, we simulated the same system, but in the bottom image, but instead of having 500 grid points that we're simulating, we only used a 50-point partition of the unit interval. And then you can see that despite the using only 1/10 the number of grid points to simulate the original 500 node system, if we use the 50 node partition, it still has the same general trajectory of the system. So I've been throwing around the word approximation a lot, but it would be nice if we had some instances where we can explicitly solve the full value of the system. And we're going to look at one special case where one special class of graphon systems where you can do that, which are these low rank graphon systems. So here, when you have an L2 operator, A with a finite number of eigenvalues and a finite number of eigenfunctions, then you can actually write the operator A acting on some function f just as this finite sum of the eigenvalue times the projection onto each of its eigenfunctions. So when you have your operators A and B, and one of your operators A and B are low rank, and your Q-noise covariance operator Q is also low rank, then you can efficiently calculate the graphon limit. Now, the interesting thing is that when you have a finite rank adjacency, or a finite graph that has a large number of nodes, which are generated, which when you look at the adjacency matrix in the limit, has a low rank graphon, you can approximate the finite graph system with the low rank graph limit very well. So we're just going to write some assumptions in notation. First, we're just going to state that there are a finite number of orthonormal L2 functions denoted f here from 1 to n, which span a particular space, subspace S. And the operators A and B are finite rank with respect to the invariant subspace S. And that means that whenever you have this any function v brev here, which is in the orthogonal complement of S, then A operating on v brev and B operating on v brev equals 0. Now finally we have an assumption that the Q noise is also finite dimensional, and it also has representation on the subspace S of this form given here, which is equivalent to the Q operator being low rank with respect to S. So when we have these low rank systems, we can decompose them into two components. The state can be composed into this XF, which is the part that is dependent on the linear subspace S, and this X brev, which is the orthogonal component. And furthermore, you can do the same for both U and by definition, W has this low rank behavior. So for low rank systems, the part along the eigenfunctions and the orthogonal complement satisfy these two differential equations. On the top here, you have this term along F along each eigenfunction, and on the bottom you have the orthogonal component, which is entirely diagonal and indeterministic, and you can actually express it explicitly for each index alpha just with a single constant e to the at for alpha, x brev initial condition of alpha plus the control input locally. So for one of our orthonormal set of basis vectors, orthonormal set of basis vectors, we can actually just write x and u into a finite dimensional or a finite dimensional vector. So here we can just turn this function defined on the unit interval into a vector of projection constants onto each of the orthonormal basis functions, and we can define our matrices A and B entry-wise again just by these projections onto each basis function, and then this gives you a low dimensional or an m-dimensional vector system here, dxf, with this m-dimensional initial condition x naught. So we're going to look at one particular a one-dimensional example of this behavior, we're going to use the graphon A being this being rank this term alpha squared minus 1 beta squared minus 1. So this has the orthonormal based function phi, which is what you get just by taking f and dividing it by the norm, and you decompose the full L2 state x into a constant along the phi dimension plus the orthogonal complement, and here this is just and here you have this one-dimensional differential equation along with this linear differential equation that is fully diagonal and deterministic. For initial conditions, we're just going to say that x naught is a signed function along the unit interval, and an x naught phi is just the projection of the sine function onto phi, and the x rev is the initial condition minus the projection onto phi. So we create our adjacency matrix of 300 nodes, sampled from this low rank graphon here on the right, and we see that on the left we have this this complicated non-smooth adjacency matrix where it's not, there's obviously the top left is more connected than the rest of the system, but it's not clear what behavior this system has in the limit necessarily. And this adjacency matrix here, because it's randomly constructed, is actually nearly full rank. I believe it is ranked 299 out of 300. But first, when we just run our graph averaging system here on the top left, where the vertical part is the state, then we see this one particular behavior of the system for a given Q-noise trajectory. And if we do our standard limit approximation by taking the unit interval and breaking it into 300 grid points, for example, and evaluating our graphon at each combination of grid points, we do have a very strong simulation of the system, and you can see that the state error over the time of the system is growing relatively slowly, even for a relatively small graph of 300 nodes. But when we have the system decomposed into our component along the one rank phi, we actually see that the system has nearly an identical trajectory as the original finite graph system. So on the top left, we have the trajectory of our rank composed system evaluated as a one-dimensional linear differential equation with a orthogonal complement. On the top right, we have the evolution of the component along the eigenfunction here. And the bottom left, we see the deterministic or diagonal orthogonal component evolving over time. And we see, if we look at the state error over time from the root state error over the spatial indexing of the finite graph system and the low rank graphon approximation, we have a similar mean root error evolution over time. So this means that even though the system is well established or is well approximated by the low rank system, even though the graph is very complicated. So our final topic is we're going to talk about these dynamic stochastic games on graphons. So we're going to move to discrete time graphon field games, which are distinct from the graphon mean field games that Peter's lab has been working on the past few years. So graphon field games, here they're discrete time. Most notably, each graph contains one player instead of interacting with the mass of players at the on other nodes through the graph. And there is a Q-noise disturbance on the entire graph versus each player on each node being affected by a independent Wiener process. So when we have our Q-noise can be simplified to just in a very straightforward manner. We just replace our collection of Brownian motions with a collection of independent standard normal random variables, here denoted epsilon. And instead of having a time indexing, we just have an indexing of k. And because these are independent, then we have this discrete time infinite dimensional Gaussian process for each k. So when we have we're going to look at a graph field tracking game where each node is trying to match the state of its neighbors. So here, instead of having a graphon A operating over the system, we're just have a local state feedback A times the local state xi for each I, plus a local control, plus some constant d times this average over the graph adjacency matrix M of all other states, plus the ith index of your discrete time Q noise. And each agent is going to optimize the objective function of this quadratic term for each I, you're trying to match your neighborhood against the best responses of all other players. Now, this is a very complicated game to solve because when you modify your control, you're affecting the states of all other nodes directly. So it's just not tractable to solve this directly. So when we have a graphon field game, we just take the limit as the adjacency matrix M, Mn goes to infinity, and we replace it with the graphon, this bold M. So instead of having this finite sum for sum, we replace it with Z. So which is just the operator M acting on these states of all other players X. So we call the Z here the local field. So the objective function that each agent is trying to optimize is this J of alpha, where you're trying to match your state to the local field at each time step without spending too much cost. Where Fk is just the filtration generated by the state of the system X and the state of the field Z. So this was accepted to the 2023 Conference on Decision and Control, but it turns out that you can actually find a optimal strategy for each agent alpha explicitly as a local feedback F multiplied by your local state X plus and some operator here I write it as H operating on Z, the state of all local fields, the local field for all players evaluated at alpha. So this proof has 2 steps. The first is we assume that we have some arbitrary stochastic process V that we're trying to track, and we find the solution using dynamic programming. And this turns it in from an infinite dimensional problem over all players at all times to a one-dimensional dynamic programming problem. And then we're going to use the condition that the local field Z is defined as the operator M acting on X, which we call the consistency condition, to show that when the stochastic process V that you're tracking equals Z, then you can explicitly calculate the feedback solution or a feedback strategy for all players. So the dynamic programming approach is relatively straightforward. You just start with your standard definition for a value function, and you here where you have the stage cost plus the costs one step into the future, and then you, along with your terminal condition, and we make the ansatz that there's some local term multiplied by this pk, which is going to be a one-dimensional term, plus some quadratic parts of x of alpha acting against this offset s of s alpha, plus some constant offset. So the important part is we need to find this offset process S alpha to calculate the optimal control. So what ends up happening is that when you apply the ansatz to the dynamic programming equations, you end up with these difference equations right here. For these 4 equations up here are all one-dimensional real constants. And the offset process, which is the tricky part, is the one depends on the signal V that you're trying to track, and the expected value of the offset process one step into the future. So you can actually evaluate these with the terminal conditions P of t equals S, and the offset process is given by offset process terminal condition is given by the terminal condition, the terminal value of your stochastic process that you're trying to track. So you can, in the most generous terms possible, find the optimal control in terms of your local state, the process you're trying to track, and this expectation of the offset process S one step into the future. So the difficulty with finding this U is that you don't know the sequence S, and in general, you don't have a solution for these stochastic processes. However, because we're working in the graphon world, and we know that the process V is exactly equal to Z, which is exactly equal to the M operating on X, then you can explicitly calculate the expectation of S one step into the future. And this is a typical mean field argument because here, your personal inputs do not affect your field, because you're connected to an infinite number of players. Then you don't have to then the only requirement is that your controls generate a consistent local field Z. So it actually turns out that when you make this assumption and you use the terminal conditions for S as being M times the terminal state X, you can actually find the operators that let you calculate the optimal control U here. So just as a very quick numerical example, if we have a Graphon field game here defined by the equations x of k plus 1 equals 1.1 xk plus u plus zk plus w, then and z is given by this integral over cosine of the cosine graphon on acting on xk with the objective function 2 times x minus z alpha squared plus u squared. Notably, this, because the a is greater than 1 and it's a discrete time system, the system is unstable. And Q has the uniform attachment graphon covariance divided by 10, because if the covariance is too large, the system is just dominated by noise. We can actually see that on the top here we have the state of the agents over time from k equals 0 to k equals 30. And we can, on the top, in the middle, we have the local field at each node. As you can see, it's being operated on by this cosine function. And on the bottom, we have the difference between the two simply at the terminal time. And as you can see, the difference between the two for the most part is relatively low. So we say that the system, particularly through the middle indices towards the end, tracks the tracks the local field well. All right, so finally, just for a few future directions that we're looking into right now, we're going to move from complete information feedback to partial information. Specifically, we need to look at, for linear graphon systems, we need to look at the observability of these graphon systems in infinite dimensions, and in low rank, and in particular, we're interested in these low rank observations of these infinite dimensional systems, and as well as just applying the Kalman filter and showing that the Kalman filter will be a convergent observer. And finally, for Graphon field games, we're going to try to extend them to continuous time games, like in the standard Graphon mean field games setup. And we're going to explore the relationship between the Graphon field games and the Graphon mean field games, and in particular, the actual impact of having an infinite number of players at each node into the behavior of the system. All right, that ends my presentation. Thank you for your time.